Hey everyone, my name is Taylor Sparks. I'm the editor-in-chief of Integrating Materials in Manufacturing Innovation. We have a new paper to talk about. It's called Multiscale Model, Predicting Site-Specific Texture Evolution and Application in Two-Phase Titanium Alloys. It comes from lead author Benjamin Begley from Victoria Miller's group at the University of Florida. And coming from Florida, we shouldn't be surprised that they named their software Pirates, right? Process scale, industry research, automated texture evolution simulation. That's right. This software is about tying microstructure and site-specific crystallographic evolution to the actual deformation process that causes it. They point out that the way that's typically done in the past is by linking finite element software with crystal plasticity models, and they've got a new way to go about doing that. First and foremost, they say that forming materials is challenging because if you can do hot deforming, yes, it's going to change the shape of the part, but that's also going to change the microstructure. And you want to ideally control both of those things. And that gets especially challenging in some alloys like titanium, alpha plus beta alloys. If you're familiar with these family of alloys, the alpha and the beta phases have very different mechanical properties, right? And due to the strong plastic anisotropy of this alpha phase and the difference in the flow stresses for these two phases, it becomes hard to actually predict what that final phase is going to, final microstructure is going to look like. It is possible though. They point out that people for a long time have done finite element modeling, which will give you the stress and strain state throughout the parts. And then if you have that, you can couple that to things like crystal plasticity models to do this. And in fact, it's been around since longer than I've been alive, clear back to 1982, the first one. In fact, people sort of one of the state-of-the-art tools here that inspired their work is this Damask, right? The Dusseldorf Advanced Material Simulation Kit, which you can see is here. Now, this is a full field solver for crystal plasticity. And full field's pretty awesome, right? It says it can capture complex deformation behavior in the grains, including fracture mechanics. But being full field, it is computationally challenging, which means they typically look at small volume element sizes. On the other hand, there's always mean field crystal plasticity modeling, right? They point out here because it's mean field, the grains are treated as having no spatial position, but are instead each treated independently as an Shelby inclusion within the homogeneous effective medium, which has the average constitutive properties of the aggregate. So in this work, they're going to essentially look at a computationally efficient way to integrate crystal plasticity with these finite element simulations and try and demonstrate that it has utility in predicting microstructure evolution during hot forming by looking at a case study in alpha plus beta titanium alloys. Here's an overview of the flowchart for the software itself. You can see that you obviously need to know what your deformation process is. You obviously have your user-defined modules. These are going to be related to the material itself, things like the microstructure or your plasticity parameters. These can be taken in together in your VPSC model to ultimately give you site-specific texture evolution. Now, one of the key hypotheses that they're sort of setting out there is they think that they're going to be able to predict the local microstructure during this process by simply providing a few key parameters that are both time and temperature dependent. So things like the phase fraction or the crystal resolved shear stress. That if you know those, that it's going to be sufficient to do these predictions without necessarily doing the full field crystal plasticity model. All right, how do they go about testing it? Well, they're going to take rolled Ti-6-4 specimens for these materials. They got them actually from ATI, right? Now they can do simulations on these materials. The materials themselves actually underwent 2 and 4 pass unidirectional rolling. They were done at 2 different temperatures, 760 and 870, and then they'll be able to actually look at the microstructure evolution via things like EBSD at different spots, right? At this ND offset position, the center position, and the TD offset position, so the nominal versus the transverse direction of the rolling. They use deformed 3D finite element simulation on a workpiece of the same dimensions, which allowed them to do these types of comparisons, where you're able to look at the different position in the center, TD offset or ND offset at the different temperatures, right? Whether it's a 2-pass or a 4-pass, to get these pole figures to essentially analyze the texture that's being arising within the material in these different regions during deformation. Importantly, right, the key figure is how well it matches the actual EBSD or sort of experimental pole figures. And you can see that they're actually able to model it. But the original Pirates versus the Pirates that takes into account the transformation texture gives you very different results. They see better agreement if they use the model that accounts for transformation and texturing. Some of the key takeaways I get from this paper is, first off, they show that a loose coupling between finite element and crystal plasticity is sufficient in some cases, right? They basically point out that if you have this temperature and time-dependent properties, and you couple that with a VPSC model, even a mean field model, you can get pretty decent simulations. It says, given the relatively simplistic CRSS and phase fraction parameterization, so that's a pretty simple model, right? The extent of similarity seen between experiment textures is sufficient for users to make informed decisions about the site-specific texture evolution while planning their forming operations. So a useful tool during the planning phase because you don't have to invest massive compute into it and you can get reasonably useful information out of it still. And then lastly, to point out that the implementation of a module that updates the crystallographic texture base, considering phase transformations, actually significantly improves the accuracy of this modeling. So what do you think? Check it out yourself in the latest issue of IMMI.